this video we are going to discuss about the topic called nano biomimicry. So what it means, nano means what, bio means what, mimicry means what, all these topics and all these contents, concepts and all we are going to explain in this video. So this is Dr. P. Vishnuvaradhan from Department of Biomedical Engineering, Sri Ramakrishna Engineering College, Coimbatore. So this is the first slide where we can see this title I have given like nano biomimicry. Nano means you all know where we can see materials which are in 10 to the power of minus 9 scale, means like from 0 to 100 nanometers in the scale. So which are some things cannot be visible with the naked eye. So those things can be visible through from microscopic there are some special equipments to see those things which are not can be seen by the naked eye. So those equipments are called scanning, electron microscopy and TEM, all these things and all. So we are not going to much deep in that, but we are just we are reading about the biomimicry, nano biomimicry. So first of all we have to know what is biomimicry. Biomimicry, the word says bio means from nature. We are going to learn or we are going to mimic whichever is there in the nature and environment, and those examples we are going to take and mimic as it is, not in 100%, maybe it can vary from 50 to 80 or 80 to 90%. We are going to mimic those things for our daily life usage applications. There can be what it can be. In this video itself we can see this pen or is also is mimicked from nature, environment, etc. All these things, even this watch, all these things, the textiles, all these things has been mimicked from the environment. Those are called biomimicry. And how this nanosciences uses biomimicry? See, there are many examples that this nanotechnology is only to one uni division or uni discipline. Nano can be used anywhere else. Even the nature is made up of from nano materials. Small, it's like we have two approaches, which is like bottom to up approach or top to bottom approach. So whereas the nature is always mimics the bottom to top approach. So that is what from self-assembly things, self-assembly we have a concept like self-assembly. So where small tiny particles combine into make into a big particle or big material or big thing. So likewise we can say the nature always will depends on top down bottom up approach. For example, I can say you the best example how the building has been built. So small bricks will be taking and assembling them and pouring cement and making into one big building like this. So that is what bottom up approach. So that is what nanosciences uses in biomimicry also. The best examples we can see gecko. Gecko is a small animal where it can stick on the walls and climb on the walls, like the best example Spider-Man. So likewise that, and moth eyes, the moth eyes can be a bigger and it can be visioned in various types of things like UV vision and infrared vision and black and white, all these things can be visioned, and clearly they have photoreceptors, many photoreceptors, not upon when we base it on human eyes. They are very much developed, advanced, so they can see small insect or they can see whatever is happening, predator is coming around this 360 degrees Celsius. There are some animals like they can view the 360 degree angle throughout what is happening in their surroundings. That example is called nothing but there is an ocean called maritime something. This is called. We'll see in the next slides. And butterfly wings. We have many species of butterflies here on our earth. So it has the species is differentiated based on the colors of the wings, and that colors of the wings can be used for our daily day-to-day lives, like windows, making windows, colorful windows, all these things. And also there are some solar panels we are using where we can synthesize, or we can make the design like butterflies wings, and peacock, the same peacock or feathers are also are used for us to use the solar panels on our roof of the floor. And lotus leaf, the main lotus leaf having an concept called water repellent or hydrophobic. This can be used for painting purposes, where we can repel the water. So it is called water disc-like applications and all we can use. And then tonkan beaks, so where we can be using as a hammer to nail on the wall, to nail the wall on the wall. So hitting on us, and also these things. There are many examples here, etc. There are many examples we are going to teach in these coming up slides. So the biomimicry definition says that most of the problems humans face today are also faced by other organisms. Over the course of evolution, we are having generations and generations, the evolution, the nature will adapt to the environment, and it will restrict, or it will gain resistance, and day day it will be advanced and developing from the surroundings things. So they will evolve, and organisms gain more efficient ways to use the environment. So likewise humans also, we are using the environment likely, and then we are adapting environment, and we are living our life in our own way, sophisticated way, or whichever we can say that, or luxurious way. It is all about environment based only. And the organisms that are alive today are the successful models for products of evolution. So there are the organisms we are mimicking and developing a products which, and then we are going to use them for our daily day-to-day life purposes. So that is what they are. They are stood like role models, and we could learn a lot from nature when it comes to solving our challenges in a sustainable way. When we are designing one product, for example, we'll take a bullet train. Yeah, it has been developed from mimicking the kingfisher bird. So this, because it go very fast, 360 kilometers per hour. Likewise, we have taken that one factor, and the structure of the kingfisher body shape, from that we have taken the same shape, almost not like 100%, almost similar shape we have taken. We have designed our manufacturers have designed the bullet trains, where it will go 360 kilometers per hour or 350 kilometers per hour. So the same products, and if there is any advances, if the kingfisher, whichever it has an biggest advantage, we don't know whether it can go into the ocean, or it can land at a time into the tree, onto the tree. But all these things we are taking, and we are making advances in our product. All these things we can learn more. This is another example. We can see this is called eagle. So from this we have mimicking so many things. Even the eyes, from the top it can see it can fly top of the sky, where the other birds cannot fly. There is one spears and layers, but eagle bird can go into that layers, and it can see the vision also is very good. From there you can see one thing, the eye vision also we can copy from the eagle. And its wings are very rare, which like when you compare it to other birds, usually the other birds has to tap repeatedly, it has to fly, but eagle need not to tap many times, it can stay for long. Likewise, and it can be in the sky itself evolving all these things. Likewise, we have developed for our day-to-day life is aeroplane. Almost similar structure it has. We have the wings over here, and it can be stay long for the in the sky, and ergonomics all we have been studied of this eagle, from the eagle, and we have developed an aeroplane based on that. This is called one biomimicry, which we have human beings has been evolved from the nature. So another thing, nano in nature is called gecko-fit, as I told you before the beginning of this video session. So the gecko So this is a gecko animal. It looks like lizard. It's a type of species where you can see it can stick to the floor or to the ground for a long time, and also be using that feet. This is called gecko feet. Gecko feet. So using this gecko feet, it can climb on the walls and it can stay for a long time there itself. So from this, what we are copying is one more question over here. So if you see macro and meso and micro, we know that what it ranges tells that. So less than 2 to 50 nanometers are called meso, and macro is greater than 50 nanometers, and micro is less than 2 nanometers. Ranges of the scales, you can see the scale area, cetal area between this gecko feet, you can see. So it depends on various species contents. So if you have, so this is one type of species which will be having a micro, the distance between these two cetal area will be more than 50 nanometers, and whereas for meso, there are other species like they are having the range between 2 to 50 nanometers, the scales between the cetal area, and then the micro species, they will be having less than 2 nanometers. So these are all the same images which has been taken, the single theta. So you can see the layer here, this layer can be a micro or meso or micro, all these things, and 1,000 spatula strips, all these things. From that strip you will be having a small hairy like structures. So this, because of this nature it has, it can hold for on floor for a long time, it can stick for a long time, it can climb on the floors wherever, it can go topper, all these things. So this type of species which having micro can go a little bit higher. It cannot go much higher because the single theta between this feet will be having that much not holding capacity, it cannot hold. So it can go up some to heights and then it can fall again back. So likewise the figures, but the meso, the species whichever it is having, it can go a little bit heights more than the micro animals can go. So it can go there and it can stay there for a long time, and then coming back to micro, it can go further more heights, comparing all these things. So it is having, so this is what nano comes here, the meso, micro and macro between the cetal area. So this is the nano comes here, and the advantages is it can climb more heights. So gecko feet are covered with nano size hairs that use intermolecular forces, that is called van der Waals forces, allowing the lizards to stick firmly to the surfaces. So we have known, so by this best example we have known the nano sciences in biomimicry. This is one best example. I am going to teach few more examples in this slide. So this is what, again this same gecko can be used for science translational medicines, and in hot like patches, glue. So whenever we have it's like there is a tear in our skin or any organs, this glue, gecko glue, can be developed from this gecko feet, which is also having some glue type things to stick up. So by replicating, this scientists have developed an adhesive tape that can seal wounds, so it can patch up the wounds like this. If you have a cut, so we can make it the glue here and it can seal the wound, or patch a hole caused by the stomach ulcer. If we have stomach ulcers, if you have stomach ulcers, you will be having a patch between that, and we can use this glue or patch to stick up that layer there. And the adhesive is elastic, waterproof, and made of material that breaks down injury heals. So this is an adhesive they have made, another one, not only climbing the walls and going wherever to the heights. Even you can see the best example in real time. There is one sports called climbing, where the The sportsmen can climb the big rocks, mountains and all. This is what they'll put the hooks onto the shoes. Even there is one more application, Jacko shoes. In the next slide we'll be having. So it can we can adhesive to the mountain and we can climb likewise with the rope head. Those sports also there here. This is one more example. This can be a light activated for further advances. We have done researches has been done for our further advances. So when the UV light is focused on that adhesive, it can be having two biomolecules where it can be activated by using UV light. The two biomolecules are glycerin and an acid. So wet and also wet adhesive, even in wet conditions also it can be adhered to that patch where to heal the wounds which we are having in skin or in organs. Many adhesives lose their potency in the wet environment, but this adhesive has one does not. The tissue surface need to be dry. The tissue surface should be need to dry. The adhesive works on the presence of blood without reacting chemically. The best example, if the audience who are not in biological discipline or area, the best example I can say, puncturing, when the tire is got punctured, what mechanic, cycle mechanic will do, or cycle or bike mechanic will do when they have tire puncture? They will rub the surface and paste the glue and patch it and make it it can be patched for a long time until unless they will be having one more puncture on the same spot, or else it won't come out. It can be in weather conditions or wet conditions or in a very sunny conditions, doesn't matter, it won't come back. That is one more real-time example we are going to use here. And biocompatible patches, it can be biocompatible when you are going with the when we are using them in the body. So the patch is biocompatible, which cannot be recognized by the immune system and cannot be engulfed and thrown out from the body. It will be a biocompatible, means it's called the immune system will spot whichever the particles are foreign body, the immune system cannot recognize, that is called biocompatible. So these adhesives can also act as biocompatible. Jacko tape. So this is what a big SEM image, and it's see the clear image is here. Very nice image. Very nice image. Lamella is called lamellas. It will open all this inside. So very nice. This is the same image has been done on the Jacko's feet. How they are very sticky. Very small lamellas are ejecting from its feet. So number of spatula in his foot is 1 billion, approximately 1 billion spatulas you will be having there to stick on the walls. And intermolecular forces is responsible for the strong binding the surfaces. Intermolecular forces are nothing but van der Waals forces, and it's also called as electrostatic forces. A Jacko can lift 130 kgs weight. It's very big, 130 kgs. Even we itself cannot be doing the 130 kg lifting up even all these things, but Jacko using this animal can lift 130 kgs of lift. See the example over here. It can be one Jacko tape can be adhered and can use the lifting of 1 kg here itself. Very advantageous, very advantageous. And so making use of these nanostructures found in setae, the grip of shoes can be improved using mountaineering. That's what the people who are now doing mountaineering are called mountaineers. So with this application we can climb the mountain with having applications on shoes. So hooks we can, these shoes are not like that, but we can have a Jacko shoes separately and we can climb the mountains heights big. Even I think we can climb Mount Everest also by using these Jacko chips. This is it's just like jokes on the part, but really we can do that. So Jacko shoes, this approach may provides better stability on rocky terrain and prevent slipping while you climbing on descending. So there won't be any slipping. It's an it can be an anti-flipping or anti-slipping parameters will be having factors. Then scaling new heights will be no more difficult. It's a very good advantage. Jaco, we can use and now I have got one idea. We can use this adhesive glue instead of patch. When we have a skin tear here, cut, if the skins are and the inner tissues has been open, instead of using the patch, band-aids and all, we can make a glue, Jaco glue, which is biocompatible, and put it on that. So automatically the skin will get stitched up and there won't be any scars. I think we can make this in advantages in futures also without any scar generating. We can use Jaco glue. I don't have any knowledge, but it can be anywhere else. Some researchers have been done. So this is what advantage. And the one more thing is spider foot. This is one advantage we have found it from Jaco. Similarly, we have a spider. Similar things can do by spider also. It can also go heights and it can be stayed for a long time, and you can build this fiber and all these things from spider's foot. Also we can use the same advantages. So strength of the suction in the spider's foot is due to all the small van der Waals forces at the nanoscale pulling at the same time. So why isn't stuck in one place? It lifts its leg so that the stitches lift successfully, not all at once. So this also can be done. And spider, coming up spider, we also have this spider silk. It can synthesize, it can make silk from its mouth and from its saliva basically. So it can make an spider web designs, and this web design also can be used for our designing these mosquitoes, sheet, all these things. Even though the application, the parameter whichever it is having, the web, it can whichever the flies are traveling throughout that, it will get stick and adhesive to that web, and there is no more they will be stuck in one place, and by that when it gets stuck, the spider will come and eat likewise. So with this design, web design, we humans has been copied from nature to build up the mosquito sheets. Not only mosquito sheets, they will be having that design and all we can use for where filtering purpose. Yeah, filtering, we can use the filtering purpose in daily life to juice filtering, all these things are filtering cups. We can use all those things from this silk giving from spider. The other thing is self-cleaning windows from moth eyes. This is what moth eyes. It is having self-cleaning, means like it can have an water repellent, self-cleaning, hydrophobic things. If you put a water on that, it can it can clean with there is no any water cannot be absorbed, so it will be on smooth surface. It can be cleaned easily. It's for self-cleaning, energy saving, and anti-glare from moth eyes. So this is what moth eyes. You can see the layers have been designed here very nicely. They have designed here. See the gap between this and all that and all is very nice. And spiders and chameleon like material changes color on demand. The best example, changing of colors. Morning time one color, afternoon time one color, evening time one color, night time one color. So differently it has. From this we also developed shirts or textiles which can be in sunlight one color and dark one color. When you are exposed to sunlight, they will be in different colors of things that can be used. Even in windows also we can use. So this also can be used for our daily day-to-day lives for usage purpose. See here, and you will be having radiums on the road where you can see the radiums colors. When you see at one angle, it will be a different color, and when you see in different angle, when you have different color. Basically, in traveling on the roads, the radium colors normally. So when is a more sun, we can see longer vision. We can see there is some obstacle there during our travel. That is what best example. Again, we can be found out from here. Chameleon like. And antimicrobial physics from cicada. Cicada is a small like insect. The wings of this small fly display bactericidal nanoscale pillar structures. Here you can see bacterial side nanoscale pillar structures. It is also used like spider web only. It can stuck, or it can make insects to stuck there. And each of these pillars is a spike of several tens of nanometers in diameter. All these things densely packed on the wing surface. These pillars arranged into nano patterns. So you can see the nano patterns over here, which pierce the membranes of bacterial cells on contact, tearing bacteria apart. So this flies Cicada can be act like an antibacterial things. Before going into the body itself, it can have antibacterial activities here. And coming for inspiration from fish scales, from fish also we have been inspired, and we are doing a lot of things here by trapping water with the scales to create self-cleaning purpose. Oil repellent coating in paints and all will be using, and promoted part of idea behind the work. So researchers in China basically have taken inspiring from fish scales and skeleton flowers to make transparent underwater. So underwater also we can make the floor can be seen easily. If you are, for example, we have seen in some swimming pools and all, the floor can be made like this with type of tails on this. We can see from 7 feet below also we can see the floor. That is what the technology has been from made from the China. All these things, it stays clean by repelling oil. So surface will be always clean by using this repelling oil. So we make surface very clean here. So see here, before and all will be having, it's not transparent. When we use this glass here, they will be having a transparent, easily we can see the words, all these things here. From fish scales we have been copied that one, transparent things. And also we have copied the same application from the skeleton flower. It's called Diphilia grayi. So from this also we have been copied the same thing. The exoskeleton, the air skeleton flowers petals appear white, but in contact with water they become transparent. See here, this is the actual flower looks like. When it contacts with the water, it will become very transparent. So from this also we have been inspired for our usages in daily lives. When we touch in small papers also we can see in plates. In kids, when we are in child, we will be using a plate called radium plates, where we can put a water on that, it can be transparent, all these things. So on sunny days, the air liquid interface of the petals cause diffuse reflectance, and watery interface increasing light transmission, so they can transparent. This is one more example. Transparent surfaces from repelling oil, that's what I said in the in the previous slide. So repelling oil from fishes, from fish scales and all, we can be using for our self cleaning purpose, and oil repellent surface, not only the water repellent, the oil repellent surfaces also we need for our advanced technologies. We are using for in cars, transport, in automobile advantages, and all this oil repellent is used. Even in the floors also it should be oil, cannot be just poured on the water where we cannot see the oil is there or not. So it can be repelled out to find out the floor is whether it's having oil or not. Nano in peacock feathers. See the peacock having a very beautiful architecture it has, and we can see it's very designed one, how the nature has been given the colorful look for peacock. The same thing we have been copied to our windows making, in households and all windows making. We can make our beautiful glasses which can be glare or anti-glare, all these things, colorful windows. Even in solar panels we can use, I think I have kept in this video. So here we'll see. So Yoshikioka and Konista found that the pigmentation in peacock feathers, instead of reflecting light, serves to absorb the randomly scattered light and thus make vivid the interference color. So sunlight, if we get in this, it will become very the light will get scattered and it looks like a very shiny thing when the sun is exposed to these feathers. So likewise the windows has been designed when sun has been reflecting, sun is absorbed to the windows, it can be shown different colors and shiny things all be in the windows. So the nano structure of the feather we can see. So this is what the semi-image, colored semi-image, we can see this how they are designed, all these things, nanophotonic crystals. So they have their own properties to shine likewise. And color in butterfly wings, the same copy not only from the peacock feathers, the butterfly wings also having the same properties and also same look. We also taken that advantages butterfly wings of layers of nanoparticles. You can see this self-assembled wings over here in nano scale, separated by layers and layers of air. The thickness of layers change the colors that we see. So this is all about the topic which we have discussed in this video. So we will see in the next video for further details of biomimicry. Thanking you.